define it evenly. Layer 2 level, it's all going to be what? Forwarding and filtering of frames at the media access control as the medium access control, the MAC address being the key address resolution being used to forward and filter those frames. Okay, so it's not a bus or a router that is needed to handle that particular address, and it's purely the MAC address. Okay. Um, okay, so exactly what I was saying about you have switches forward and filter frames based on LAN addresses. And in this case, LAN addresses, they're talking about your MAC addresses. Routers do not form a base within this level. Okay, it's only when they only come into play when you're forwarding frames out of a given LAN. They're very scalable in terms looking at Ethernet. Ethernet very very scalable. It's just a switch, standard. Options for has the option for many interfaces. That's why when you see a switch today, you have a number of interfaces that various host devices connect to. They fully duplex in operations, which is for sending and receiving frames simultaneously. And it connects two or more segments as well by copying data frames between them. Switches only copy data when needed. That's when it's intended for them. One of the things that you don't find within hubs, okay, which is actually an indication of how one of the key difference between switches and repeaters or hubs. Okay, repeaters and hubs do not have the luxury of only switching copies of data when needed. They don't have that luxury. It's only switches that does. Okay, that's why it's a key difference from repeaters or hubs. And higher link bandwidth is always addressed. Collisions are completely avoided based on its design, and they have much greater aggregation of bandwidth in terms of separate segmentation to address sends and receive at a given point in time or at any given point in time. Great. So moving on, as we earlier pointed out, Ethernet happens to be a protocol developed by IEEE as a standard of 802.3. And it's generally consisting of your media access control layer with a composition of carrier sense multiple access or collision detection protocol, and generally moves frames towards the physical layer depending on the given layer that's the information is being transmitted from. In this case, if it's Ethernet, then we're looking at purely from the layer 2 to layer 1, and then the information leaves the physical layer as a signal, en route to a particular destination node, since Ethernet revolves around MAC, we want to look at some of the earlier implementation schemes that were developed before Ethernet became Ethernet. Okay, there were a number of implementation, basically, and as I was saying earlier during the objectives, one of them was Aloha. Aloha was one of the first implementation of MAC schemes and the Ethernet. and they had their challenges. You know, number of issues came up, then implementation. Uh, but generally, you would say Aloha was developed as or for packet radio networks, uh, but its application as a shared transmission medium had issues. Aloha was purely designed um, to transmit frame at any given point in time where stations listens to an amount of uh, or listens for an amount of time which is usually equal to the possible round trip of propagation delay within a given transmission time. And when there are no requests on that particular or transmission on that particular medium, then a particular host is allowed to forward information across it. And obviously, there are going to be challenges if we were to look at the way Aloha was designed. It was just taking information in as and when the medium of transmission was not occupied or was not being used. Now the question of what if the point at the point when it decides to forward the information, another particular host also decides to forward the information on that particular given medium. What is going to happen then is collision because there's no communication because it's a straight design concept to just allow hosts to basically transmit information based on a given time frame of listening to a particular medium. If the medium is idle, the information is transmitted. If it's not, it's not. But the problem that would happen in that scenario is what if two devices send the information simultaneously? Then you're bound to have issues. So that's one of the things that made it quite inefficient in its design. And a solution to address that was a second version of Aloha, which was a slotted Aloha, which was actually designed to improve collision issues within Aloha, the original Aloha itself. In the scheme of slotted Aloha, time on a channel was organized into uniform slots and based on the sizes of equal frames being transmitted at a given time. So in a central clocking system, there was a technique needed to synchronize all stations so they can all be allocated their time for transmitting a given information. But even in that scenario, even if you allocated time for every device to transmit, what if you have issues where a particular time slot allocated to a given node or host device expires, but its transmission has not really been completed yet, and then the turn for a different host comes up and they decide to transmit, then you're still going to have collision. I mean, although it might improve collision if you were to allocate time slots. So in this case, it's kind of like you're given. I think it's kind of like going to a presentation, and then each presenter is given an allocated time to speak. What if the allocated time for a given speaker is up, but the message that is trying to carry or convey across or the presentation is not over yet? What happens then? Do you just cut them off? and then say the person to come should the next person whose time slot is up should come in, and that will make the information being presented by the first person incomplete. So it's the same concept. If I was carrying my message across a medium within my time frame and I see the time frame, you tell me to just cut it off, then the message that I'm delivering will not be correct. It wouldn't be the entire message, it'd be a partial message, which is obviously not the same as the original message that I wanted to convey. Okay, so some of the issues that came up within the early switching standards. So with that, there was a newer transmission or scheme that was built, which was the carrier sense multiple access. Yeah, so as I mentioned, it's protocols then divided by EEE, revolving around the media access control layer, in composition with physical layer, and earlier schemes with Aloha, sled Aloha with their issues before we got to CSMA or the carrier sense multiple access. The carrier sense multiple access was designed to address um, greater transparency and collision avoidance within the earliest schemes of MAC implementation and the Ethernet. Okay. Okay, so this is where I was going through the earliest schemes for MAC implementation and the Ethernet. So here's how the Aloha was built. It was designed as a station for a station to basically forward frame as and when it has it, and stations generally listens for a given amount of time. Like I said, it was listening for a given amount of time first before it forwards a particular frame. But the issue was if two host devices or two stations decide to transmit at the same time, what happens in collision? So that's some issues that were that came up. So it's a two or more simultaneous transmission causes collision. Okay, so that was one of the biggest issue with the Aloha system developed in Hawaii, if I'm not mistaken, as a packet radio system. The earlier implementation of high-speed schemes of information transmission and the Ethernet. Okay. So receivers would okay a particular frame based on the address that was received and short acknowledgement. If not, they either ignore the frame or does nothing to it. Frames may be damaged by noise or other stations transmitting at the same time as a collision. So overlaps of frames also occurred and it caused collision as well. So Aloha generally was simple but very inefficient. It consumed radio traffic, random traffic with maximum channel utilization of about 18% of the given medium, and that was inefficient. So like I said, the slotted Aloha was introduced to address that issue, which creates an optimization of improvement within a particular medium to about 37%, with introduction of synchronization clock mechanism where you allocate time slot for a given station or node. Okay, so that improved the original Aloha. Like I said, even that is still gonna have issues with the scenario that I gave you with the speakers at a conference or presentation, allocated time slots, and somebody exceeds the time slots. What happens? So that issue had to be addressed, and that's where you had the CSMA, which was the carrier sense multiple access. Um, the carrier sense multiple access, in its design was to get stations to listen to channels, or what you call the carrier sense. Stations know whether a channel was free or not based on the listening or the carrier sense design that they had. And they only transmit if the channel was free. So collision became very, very rare because now you had like kind of like a nose that was, or an eye, a nose or an eye that was basically, an ears, an ear that was listening in on the channel to make sure uh, mediums were not occupied or being used before transmission uh, came through. Keep in mind the key thing was there was channel. They were allocated channels. Okay, so in this scenario, instead of having like a road with a single lane, you actually had many lanes now, and each all with lanes. You had the roads with lanes now, and the lanes were uh, properly well structured, and stations that needed to use those particular lanes or channel had this sense or ear to basically uh, sense what was going on in a particular channel before they actually send a transmission through, send a frame through. It's kind of like on a road where you have lanes and you have uh, an an entry ramp coming onto the lane. It's the job of the driver from the entry ramp onto the main lane of the particular road to make sure they are aware that that lane they're getting onto is not occupied by a vehicle, or there was no vehicle or traffic on that particular lane before you get on it. You can think through this yourself. If you're driving or in a car and you were about to make a turn onto a particular lane, before the driver makes a turn, they don't just get onto the lane. You know, when it gets that turn, they look out for traffic or cars or vehicles or motorists um, plowing that particular lane before they actually let go of their brakes to enter into a particular lane. The same concept with the carrier sense multiple access. They have to sense for the traffic nature of that particular lane before uh, they send a message through. And that became much more efficient in terms of addressing collision. That collision only happens only if two or more stations attempt to transmit at the same time on that particular channel. Then you'd have collision. Okay, so yeah, there's going to be bound to be collision, obviously, even with a well efficiently designed road with lanes and all the road sign. You're still bound to have some accidents here and there. It could be negligence here and there. But generally, uh, the traffic signs are designed to maintain some kind of order. You know, to minimize collision. So even though they were a collision, but they were quite rare, it was just few instances. So the carrier sense was a good solution to handle the early implementation of MAC scheme for Ethernet. Okay. Um, a number of implementation went with it. In traditional LANs, propagation time was usually much less for frames. So all stations know that a transmission has started almost immediately by the sense. So it's like their senses in terms of how they read to or hear the medium was quite robustly designed or efficiently designed in such a way that they could hear from afar, uh, or even the slightest hint of lane transmission could easily be sensed by the carrier to make sure that they don't send frame to cause transmission. Okay, stations usually first listen for clear mediums, which the carrier sends. If the medium is idle, then it transmits the frames. If two or more stations start about the same time instant, there will be a collision. So to account for this, the station waits for an acknowledgement. So another implementation to make the carrier sense much more efficient was that when they sense the medium, the carrier, they wait for an acknowledgement first before they actually transmit. If there's no acknowledgement, it means that the depending on the time that the acknowledgement comes through can either determine whether the medium was free for transmission or not. So that's a pretty great way of handling uh, the carrier sense. You wait for an acknowledgement as you sense the medium. So it's kind of like you send a message across the medium, checking to make sure, hey, does anybody have any frame to send? If acknowledgement comes back and says there's one or two people who says they have information to transmit or already have a transmission on the way, then there's no need for that particular station or host to transmit their frame. They just have to hold on until the medium is clear. So what should a station do if the medium is found to be busy? Well, three different approaches were implemented, were put across. One of them happened to be a non-persistent carrier sent multiple access. The second one was a one minus persistent carrier sent multiple access. And then the third one was a probability persistent carrier sent multiple access. So these were kind of like approaches to address how a medium status was before any transmission could be sent through, which is quite efficient, especially when it comes to the non-persistent one and then the probability one. And as they move on, obviously there were drawbacks in non-persistent. That's why they had to be improving it to get to the probability persistent carrier sense multiple access. With the non-persistent, the stations wishing to transmit would have to listen to the medium and obeys the following rules. If medium was idle, you transmit. Otherwise, you move on to the second step, which is you observe the medium's busyness, wait for an amount of time drawn from a probability distribution, and then you go back to step one, where you sense for the idleness before you transmit. Now, the use of random delays reduces probability of collision, obviously. If you consider two stations become ready to transmit at about the same time while another station is in progress, if both stations delay the same amount of time before retransmitting, then both will attempt to transmit at the same time, and that could cause collision. So the drawback was capacity was wasted because mediums would generally remain idle until the end of a transmission. So I guess there was point out that the non-persistent had a way of creating higher capacity medium or delay for given stations to transmit the information. And if you're looking at a high-speed transmission, if you're going to have something like this, then you might as well forget about calling it high speed, because the whole point of being a medium being high speed is to make sure that the capacity of a particular medium is efficiently managed and highly improved in terms of how either frames or packets or whatever sent through uh, are significantly managed. Okay, so the other approach um, was the one minus persistent design. So I've gone through this. Yeah, which was when you had to wait the non-persistent. Okay, so the drawback was capacity was wasted, basically wasted capacity. With the medium, and since we want efficient high-speed transmission, we cannot delay the medium. Otherwise, there'll be a defeat in what we consider high-speed transmission for high-volume uh, transmission mediums. Okay, so the next approach was the one minus persistent carrier sense multipliers, and that was designed to avoid the idle time. So obviously, the non-persistent had idle issues, which was increasing or wasting capacity. So the one persistent was the solution to address that. Uh, uh, within the one minus persistent, station wishing to transmit would listen to the medium and obeys the following rule, just like the way the non-persistent also did. The medium had to wait. Okay, the medium had to wait for an idle time, transmit, otherwise move on to step two. When step two, the medium is busy, the medium was busy, then the carrier sense will still, or the station will start to continue to wait and keep listening for a general sense of idleness or an acknowledgement of idleness before transmitting. Okay? Now, the one persistent stations are pretty much, in a way, selfish in the way they handle the transmission. If you think about waiting, so in other words, even if a station was using a medium and it had completed its frame transmission but did not introduce or show or send an acknowledgement, then it would mean that that station would probably uh, kind of like monopolize the medium, and that could cause a lot of delays uh, within a waiting period. So in that sense, a medium could be considered selfish because they were practically, if the medium was not efficiently designed to handle acknowledgement, which you would have in some systems in the early days that were not designed very efficiently, then they could basically monopolize the medium. Uh, Imagine those early days if you had the way hackers do. Hackers flood a particular medium with attacks, which is a form of selfishness by capturing an entire medium and making it completely busy, or what you call denial of service, especially if a hacker wants to really, really make your network pretty, pretty crappy or really make your network very, very unreliable. They send a denial of service, which is a DDoS uh, frames or packets on your media, on your system, and basically flood it up so you wouldn't have access to the medium. And in that case, it becomes practically selfish. So in a way, the one minus persistent CSMA was kind of like that. Essentially, the station decided to be a hacker. If it was a hacker station or a hacking station, then you'd have issues like that where acknowledgements of denial of service would never come true. So it was just taking up the resource of this particular medium without allowing anybody else. Okay, so in that case, you have drawbacks. If two or more stations are waiting, obviously, you're going to be waiting for eternity.